This is the second of three videos where we'll be using integrals to compute volume. In this video, we're going to compute the volumes of rotational solids using the method of washers. For this, we will go through some notes. Then we will answer examples 8, which is 3 parts A, B, and C, example 9, and example 10, which is the FRQ that we've kind of been working on over the past couple days in class. And this will all be happening in your 5.2 notes packet. So let's start with the method of washers. The disk method, which we covered in the last video, and if you need a refresher, I recommend that you go back and watch it, can be extended to cover solids of revolution with a hole in the center by replacing the representative disk with a representative washer. And it's called a washer because of the little metal disks that engineers use called washers. They're spacers. And so revolving a rectangle about an axis forms a washer. If little r and big R are the inner and outer radii of the washer, and W is the width of the washer, then the volume of that washer is pi times big R squared minus little r squared times W. So let's just take a look at the picture of it. If this is my representative rectangle here, and I know that there's going to be some space in here that will give me a hole, right? Like all of this space in here, when I rotate over my axis of revolution, is going to give me a hole. And so I need to be able to represent the length of my rectangle, which is going to be here, by taking the length of the big radius, which is r, and the length of the little radius, which is little r, and subtracting them. So this is actually going to be big R minus little r. And then if I take this rectangle and I rotate it around an axis of revolution, which is still here, and you should still recognize that the width is parallel to the axis of revolution, and this long side of the rectangle is going to be perpendicular to the axis of revolution. But now we've taken it, and so that it doesn't actually necessarily need to touch the axis of revolution, what you are going to get is you're going to get a disk with a hole in the center. And so we can actually calculate volumes that way too. When you take this rectangle and you rotate it around the axis of revolution, this is the solid that you get. So notice you get a cylinder with a hole in the center, and the hole in the center is what makes it a washer. And to see how this concept can be used to find the volume of a solid of revolution, consider the region bounded by the outer radius r of x and an inner radius little r of x. And if the region is revolved about an axis of revolution, then the volume of the solid is now this instead. So before, when we had the method of disks, it would just be the volume equals the pi times the radius, or pi times the integral from a to b of that radius function squared. But now that we have a hole in the center of it, we're going to take the bigger radius, which is big R of x, and we're going to square it, and we're going to subtract out the little r of x squared. And that's going to give us the volume of the washer, or the volume of a disk with a hole in the middle, or with taking out a piece of the center. So let's start example 8. And so let R be the region bounded by the graphs of y equals 1/4 x squared, x equals 0, and y equals 1. Compute the volume of solid formed by revolving R about 3 different pieces. First, we're going to do the y-axis, the x-axis for the second part, and then the line y equals 2. So that should pretty much cover the 3 cases that we did in the disk method, just in this example. But now we're going to use washers. But actually, for part A, we might actually need to use a washer. We might still be able to use a disk. So if we look at our graph of y equals 1/4 x squared, this is the graph of y equals 1/4 x squared. And I notice that if I draw my representative rectangle so that it's vertical, I should notice that the long side of the rectangle is actually not perpendicular to my axis of revolution, right? Like if this is going to be r, this is not going to be perpendicular to this axis of revolution. It's actually parallel to it, which still uses a method that we haven't covered yet called the method of shells, which will be in the third video of 3. So when this happens, I need to take my rectangle and I need to rotate it and make it a horizontal rectangle. So this should be my rectangle. Okay, and whenever we take our rectangles and we flip them, or we have horizontal rectangles, we're going to have to solve for x and change the limits of integration. So I'm going to take, and this is actually going to be a horizontal rectangle. And if you notice, since there's actually no space in the middle, this is still going to be a disk. And since it is horizontal, we're going to take y equals 1/4 x squared, and we're going to solve it for x and find new limits of integration. So when we do solve this, this turns into x equals the square root of y, or the square root of 4y. I'm sorry. Um, and we're going to have to find new limits of integration. So if I notice, I have my graph going from 0 here to the line y equals 1 up here. And so I'm actually going to integrate from y equals 0 to 1. And since this is a disk method, I can just say that my volume, just like we did in the last one, just as a little bit of review, is pi times the integral from 0 to 1 of this function squared. So this is my radius function, so it'll be the square root of 4y squared dy. So volume equals pi times the integral from 0 to 1 of 4y dy. If I take the antiderivative of 4y, I should get pi times 2y squared. And I'm going to evaluate that from 0 to 1. And I don't need to plug in the 0. So what I actually get for a volume of this rotational solid, which would be a paraboloid, will be 2 pi cubic units. Okay, that's just a little bit of review, understanding that we couldn't use a vertical representative rectangle, we had to use a horizontal. So we flipped it, and then we solved for y, or solved for x, and we found new limits of integration. Let's take a look at one that actually does use a washer. So we'll use this same graph with same equations, going back to y equals 1/4 x squared, and use the same region, but now we're going to take it and we're going to flip it over the x-axis. So it's going to look like that. Okay. And when I take this and I flip it over the x-axis, I should realize that if this is going to be my representative rectangle, and I'll use a vertical again, okay, when I do flip that, the rectangle will get smaller as we go along. And so what I will end up having is I will end up having a hole in the center of the solid. So what I do know is that I can calculate this inner radius, which is going to go from 0 to this bottom part of the curve, which is going to be the 1/4 x squared. So my inner radius is going to be y equals, we could say x squared over 4. And then I know my outer radius, which is going to be the line y equals 1 up here, and it's going to go from 0 to that. So my outer radius is y equals 1. And so to calculate the volume of this rotational solid, which would be a washer, I can say that volume is going to be equal to pi times the integral, and we're integrating from 0 to 2, since we're going on the x-axis, of the outer radius, which is 1 squared, or the outer radius squared. And why don't we separate it a little bit? Dx minus pi times the integral from 0 to 2 of the inner radius, which I know is going to be x squared over 4 squared dx. And then what we can do is that I can deal with the squares on each piece separately, and then since the limits of integration are the same on both integrals, I can combine it back to a single integral. So let's deal with that. Let's clean up the insides of each integral. So this will be from 0 to 2 of 1 dx minus pi times the integral of 0 to 2. And this will be x to the 4th over 16 dx. And then I can combine it back to a single integral. Also, since these share a pi, I would be able to factor out a single pi. So I can rewrite this as pi times the single integral from 0 to 2 of 1 minus x to the 4th over 16 dx. Taking the antiderivative of the inside, it would be pi times the antiderivative of the inside, which is x minus x to the fifth over 80. And I'm evaluating from 0 to 2. Since 0 is my lower limit, I don't have to evaluate it. So I can say that this is equal to pi times 2 minus 32 over 80. And when that all gets simplified out for the sake of time, this is actually going to be 8 pi over 5. And that's what my volume equals. Okay. Let's try one more. Part C. So the line y equals 2. And so I need to figure out my inner radius and my outer radius. My axis of revolution is horizontal. I'm still going to use a vertical representative rectangle. So if I draw my representative rectangle here, okay, I need to figure out what my inner radius is, and I need to figure out what my outer radius is. So I can actually start abbreviating it and cleaning it up a little bit. So I know that if I want to call it big R of x, which is going to be my outer radius, if I look at my outer radius, it goes from this line y equals 2 all the way down to where it meets the curve, which is x squared over 4. And so we will take the top line minus the bottom line. And so it'll be 2 minus x squared over 4. And then if I want to do my inner radius, which is little r of x, it starts from the top line, which is y equals 2, and it's going to go all the way down here and just touch the top of the bounded region at the line y equals 1. So it's actually just going to be 2 minus 1, which is going to be really nice for us because it's going to be 1. Okay, and so my volume is going to be pi, and we're going to break it into two integrals again, especially for this one because of this top outer radius. It's going to be a little bit harder to work with. My area or my limits are still going to be from 0 to 2, and it's going to be 2 minus x squared over 4 squared dx minus pi times the integral from 0 to 2 of 1 dx. And that's going to be 1 squared dx. All right, so let's deal with the unfortunate part, the first integral. It'll be from 0 to 2 of, when I FOIL this out, it'll be 4 minus x squared plus x to the 4th over 16 dx minus pi times the integral 0 to 2 of 1 dx. Now that this has been FOILed out, I can combine it back to a single integral. Just like the last example, I can factor out a single pi and throw it in front. So you get pi times the integral from 0 to 2 of 4 minus x squared plus x to the 4th over 16 minus 1 dx. Which, if we clean up just a little bit to help us out, it'll be pi times the integral from 0 to 2 of 3 minus x squared plus x to the 4th over 16 dx. Taking the antiderivative of the inside, it'll be pi times 3x minus x cubed over 3 plus x to the 5th over 80, and we're evaluating that from 0 to 2. Since 0 is my lower limit, I don't need to actually evaluate it, so the volume is really just going to be pi times, when I evaluate 2 in, it'll be 6 minus 8/3 plus 32 over 80. And when you simplify that all out and combine all of your fractions, what you're going to get for a volume is 56 pi over 15. The hardest part about finding volumes of washers is finding your inner radius and your outer radius, especially if your axis of revolution is not a nice line or a nice axis that you're used to, like the x-axis or the y-axis. It's really important that when you're trying to figure out these axes or these inner and outer radiuses or radii, that it's always going to be the top line minus the bottom line, or if it's a vertical axis of revolution, it'll always be the rightmost curve minus the left curve. Let's try another one. Okay, so now we have a volume of, or we have a washer, but it's actually the washer is going to be formed between two curves. But we're going to find the volume of the solid formed by revolving the region bounded by the graphs y equals the square root of x and y equals x squared about the x-axis. Okay, so I know that my inner radius, or I have my big R of x, which will represent my outer radius, and my little r of x, which will represent my inner radius. It's looking like the big R of x, or the big radius, is going to be the square root of x. So if you notice, my region goes from 0 to 1, and it's pretty much covered all the way across. I don't actually have to figure out, or I don't have to, I will end up subtracting in my integral, but to figure out this, or to figure out my upper curve, my upper radius is going to be that square root of x curve. My lower radius, my lower radius is going to be this x squared curve. We're integrating from 0 to 1. We could figure this out just by setting the two curves equal to each other and figuring out where they cross. So my volume is going to be pi times the integral from 0 to 1, and we'll do the outer radius squared, which is the square root of x squared dx, minus pi times the integral from 0 to 1 of x squared dx. So then my volume is equal to, if we deal with the squareds and then combine it, so it'll be pi times the integral from 0 to 1 of x minus pi times the integral of 0 to 1 x to the fourth, and this is a dx and dx. And combining the two integrals into one now, we know that it's pi times the integral from 0 to 1 of x minus x to the fourth dx, which, taking the antiderivative of the inside, you get pi times x squared over 2 minus x to the fifth over 5 from 0 to 1. 0 is the lower limit, so I don't care about it anymore. So this actual volume, once you compute it out, will be 3 pi over 10. No real tricks to this. Okay, let's take a look at the FRQ that we've been working on for the past couple of days. So we started off just finding the area of the bounded region with this question. I believe in class on Thursday or Friday, we actually did a cross-sectional for part C. And now part B of this question actually asks, find the volume of the solid generated when R is revolved about the horizontal line y equals 1. So the line y equals 1 is the line right up here. So this is my axis of revolution. Keep in mind that the upper line here, this is going to be my line y equals the square, y equals e to the negative 3x. I'm sorry, I have that backwards. This line right here is the line y equals the square root of x. And this is the line y equals e to the negative 3x. Okay. To do my solid of revolution, I need to calculate, or I need to figure out what my inner radius and my outer radius are going to be. So I know that I have a line that goes from here to the top curve, which is going to be that square root. And that's actually going to work as my inner radius. And then I'll have a line that goes from the axis of revolution down to the bottom curve. And this will be my outer radius, or my big R of x. This is a calculator question, so we will be able to use a calculator to do this integral. So I know I need to write functions for my inner radius and my outer radius. So let's start with the outer radius. I'm going to start from 1, the top curve, and go down to the bottom curve. So this will be from y equals 1 down to e to the negative 3x. So the way that I write that is 1 minus e to the negative 3x. So this is the distance between the line y equals 1 and the curve e to the negative 3x. The inner radius is going to be very similar. It's going to go from 1, and it's the distance from y equals 1 to the curve, the square root of x. So it's 1 minus the square root of x. Okay? And since we're dealing with vertical rectangles, I'm going to be integrating from this point here until 1. And we've calculated this point out before a couple times, but just as a refresher, I would set those two curves equal to each other in the calculator, and I would get to this point is actually x equals 0.2387. So to do this integral, and this is a calculator question, I can actually just plug the whole integral into the calculator. So volume is equal to pi times the integral from 0.2387 to 1 of the outer radius, which is 1 minus e to the negative 3x squared dx, minus the integral, or pi times the integral from 0.2387 to 1 of the inner radius, which is 1 minus the square root of x squared dx. And actually what I'm going to do is I'm just going to rewrite it as one integral to make it a little bit easier so that we can put it in the calculator. So it'll be pi times the integral from 0.2387 to 1. I'll combine each one, so it'll be 1 minus e to the negative 3x squared minus 1 minus the square root of x squared dx. I would recommend for the AP test and just in general that you just put this part into the calculator and you get a number, and then you leave it in terms of pi at the end. When you do that, what you will get is you will get an approximately 0.453 pi as the volume of the rotational solid. The hardest part about this question is figuring out the inner and the outer radii. The rest is just setting up an integral with the volume formulas that you know. That is all that we have for the washer method. Please refer back to the email for the problem set that you need to complete that I will be checking on Monday. Thank you.